This is a demo of a buffer overflow attack of the runtime stack of a C or C++ program. Prerequisites are knowledge of the C language, the GNU C compiler, GCC, and the GNU debugger, GDB. We have a very simple secret guessing program. When executed, it will ask the user to enter a guess for a secret. If the guess is correct, it will print a winning message. You have won $1 million. The program is very simple. Printing the message enter secret, and then the user would enter a guess for the secret, being read using the unsafe no-bound checking function, scanf. And if the guess is matching that of the hard-coded secret, it will invoke the function succeed to print the winning message. As an attacker, I want to be able to redirect the program to always print the winning message, even though I do not know the hard-coded secret. Maybe it's not hard-coded in the program here. Maybe it's being read from a file that I have no access to. I want to still be able to always redirect my program to print the winning message. Okay, let's see how this will work. I'm going to compile the program using the GNU C compiler, using the G option for debugging, and using the no stack protector option to disable default stack protection. Otherwise, my attack would not work. And I don't need any optimization, so I use the minimal optimization level 0. Let's just run the program as is. Entering the correct value will get me the winning message. Entering an incorrect value would not print any winning message. Now let's rerun the program using GDB. I want to list the source code. And I want to set a breakpoint at right after I do a scanf, having read in the guess. So I break at line 14. Let's run the program. Now the program has stopped at the earlier set breakpoint. Let's look at what we entered into the variable guess. And it has the correct value, what I just entered. Now to be able to create a buffer overflow attack on the runtime stack, I need to show the runtime stack. And to figure out the address of the runtime stack, I can use the info registers command. Here it has, among many registers, the ESP stack pointer, and the value is the top of the stack address. To see what's inside the stack, I can first set print memory format to be hex. Then I examine, let's say 20 words starting at the stack address. To get a better understanding of how do I map local variables into the stack, I want to print the address of the local variable guess. So the variable guess has the address BFFFF0C0, which is this address. And the variable guess has been declared to have 16 bytes. So the entire space here is for the variable guess. To make sure that it has the content of what I read earlier, LA, let's display that in string value. And sure, it does have the value LA, which is this value. Confirming that with a hex translation. The string LA in hex is 4C41. And that is indeed what we have in memory. 4C41 and the termination character. Here is printed in reversed order because we have a little endian machine. The string value is actually stored in correct order. L coming before A, and followed by the termination character. In this little program, guess is the only local variable. In addition to variables ending here, a stack frame also has a return address. When the main function has finished execution, it will return to its caller by loading the return address saved within the stack frame. Because of different compiler code generation variations, multiple fields may be inserted here after the local variables before the return address. So we need a way to identify the return address in order to carry out our stack overflow attack. To do that, we need some background understanding of a Linux executable. When you invoke an executable, the Linux operating system loader will load the code starting with a stat function. If you're running a C application, the stats function would invoke the libc stat main system function, which will in turn invoke the main function of the application. So when your main application has finished execution, it will return back to the libc stat main function. Knowing the libc stat main function is always the caller to the application's main function, we're able to tell which field contains the return address. We can take the value of each field as an address and check to see if the address is within the libc-stat main function. And we can do that by the disassemble command. First, let's try this first field after the local variables. By disassembling the address, we see that the address belongs to the function libc csu init. This is not the function that we're looking for. The next two fields do not look like an address, so let's skip them. The fourth field, let's try it out. That address is indeed inside the function libc-stat main. So we have found our field. To confirm further, let's look at the exact address, the instruction that we'll be returning to. And we found it, ending with EA83. Looking at the returning instruction and the previous instruction, we have gotten a pretty good confirmation because the previous instruction is a call instruction, the one to call into the main function. So returning to the one right after makes sense. Having identified the return address field, we can carry out the stack buffer overflow attack. We know that the guess variable is of 16 bytes. And when we read input into variable guess using the scanf function, scanf does not check for boundary, limiting the input at 16. So we can feed it with more than 16 bytes to overflow the boundary of the variable guess and let it flow into the rest of the stack frame. To be exact, we just need 16 more bytes to flow into this return address field and to overwrite this field with some address of our choice. Since our goal is to print the winning message and function succeed has the code to print the winning message, we should replace this value, the return address, with the address of the succeed function. That will redirect the main return to the succeed function and print the message we need. We can print the address of function succeed like this. To try out the overflow attack within GDB, we can just set the return address field to the address of succeed in memory. Here's the return address field. And this address is located at F0D, this is D0, D4, D8, and DC. I can use the set command to function succeed address. Check to see if it has gone into the memory. And it has. Remember, we were at the string compare function when we set the breakpoint. And we entered the value LA into the variable guess. So we shouldn't have a successful string compare, and we shouldn't go into calling succeed. Let's do an next and see what happened. Indeed, it has skipped over line 15 and into line 16. Now the program is getting ready to exit, supposedly by returning to Ming's caller, libc.min. But because we have modified the return address, let's see what will happen when we do a continue. Look, we've successfully redirected the program execution into calling the succeed function and getting that winning message. One unfortunate side effect of this hack is we've modified the original system return address, so the program cannot exit normally and created a segmentation fault. But we did manage to get the winning message without knowing the secret. Where do we go from here? We've kind of done a buff overflow attack successfully within GDB. We need to do one in normal running condition by creating an input string that, when passed to the program, will overflow the guess variable and flow into the return address field of the stack frame. So we need to do some kind of calculation here. The guess variable, as we remember started here, is of size 16. There are 12 bytes. Between the guess variable and the return address field. So we need to construct an input string that would do that. And within the return address field, we need to fill that with the address of the succeed function. Let's see how we can achieve that. Here we have a little C program to generate input for doing the attack. First, I print 16 bytes to fill the space for the guess variable. 12 bytes to fill the gap of the 3 fields between the guess variable and the return address field. And for the return address field, we put in the hex value of the address of the succeed function, and we print that in reversed order remembering that we have a little Indian machine here. Compile this print attack string program. Run this program and generate the attack string in the file. Check out the file content in hex. First 16 bytes going into the variable guess. Next 12 bytes filling the gap between the variable guess and the return address field. Last 4 bytes. The address of the function succeed. Now let's run the program. Redirecting the attack input file to the program. And we've gotten the winning message again, without knowing the secret. To reflect on the buffer overflow attack, the root cause is this no bound check scanf input operation, where an attacker can input an unlimited value into a limited space. The string variable guess is a fixed space of 16. Entering a value of more than 16 bytes would overflow the buffer. Into an intended memory space. If the unintended memory space is being used for later program execution, an attacker can craft an input to steer the later program execution to code of his choice. To mitigate this vulnerability, one common practice is to use static analysis tools to scan the C program for questionable operations, such as this no bound check scanf. One such tool is flaw finder. If I invoke flaw finder on my stack buffer overflow attack code, here's what I'll get. A warning about the scanf operation, and another warning about the parameter being used to call scanf, with the description. So, if you want to cleanse your code for potential buffer overflow attacks, flaw finder is one tool to consider. Another buffer overflow attack detection feature is provided within the GNU C compiler. Remember, when we compiled the stack buffer overflow attack code, we used the no stack protector to disable the default stack protector. If I recompile my code without this option, enabling the stack protector, Now, buffer overflow attempts will be detected and cause a runtime error. If I enter within 16 bytes to the guess variable, the program will behave normally. But if I enter more than 16 bytes, the runtime would detect buffer overflow attack smashing the stack, and the program will terminate. Because the buffer overflow attack on the runtime stack is such a common attack, the stack protector option has become the default for the GNU-C compiler. Summary: we've completed a demo of a buffer overflow attack on a Linux C program runtime stack. Here we've used the GCC GNU-C compiler options -G for debug and -F no stack protector to disable stack protection. We've also used gdb commands like list, break, continue, info registers, examine, and disassemble. We'll learn about the Linux runtime stack format, finding local variables within the runtime stack, and then finding the return address field after the local variables. At the end, we create a attack input to carry out the attack. One hint to reproduce: use the Ubuntu 32-bit images, like this one. They'll make the reproduction of the attack much easier.